Hello everyone. Today we are going to start with a very interesting topic of physics, which is gravitation. So let me first clarify this. This topic, gravitation, is a small part for ICSE students. It is part of the chapter Laws of Motion. And for CBSE student, it is part of a chapter which comes after Laws of Motion, which is gravitation. The name of the chapter is gravitation itself, but it has a buoyant force and fluid pressure, or the concept of pressure as well. So we are going to study this part separately, in a way that it applies to everyone who wants to understand gravitation in detail. So all the concepts regarding gravitation will be covered over here. Okay, nothing will be left. Yeah, you might have to study some parts a little bit more in detail in extra, and I'm sure that you don't mind that. Those who want to study only the topics which are covered in NCRT book or their textbook, uh, I'm afraid that I cannot restrict my lecture only up to that much part, because that is unfair, because if you want to study a topic in detail, then you definitely should have a chance, and this is your chance if you want to study gravitation in detail. Still, it is not as much detail as we would cover it in class 11. So for class 11, we would take the study of gravitation to another level. Okay, so this is just the basic idea regarding gravitation, and the basic, you can say, introduction to gravitation. So this applies to anyone studying in class 9 who has this topic gravitation in their books. So let's start with this topic. So let's start with the introduction first. Have you observed that satellites revolve around Earth? And they do not use any fuel for doing that. They do it on their own automatically. Why do they do that? Why do Earth revolve and other planets revolve around the sun? Why there is no random collision between the estimated 10 raised to 22 stars in the universe? What is the difference between mass and weight? The answer to all these questions and related questions takes us into the subject of gravitation, right? First, we'll study the historical perspective. Now, many of the students will have issue with this, because they will say that this is not part of our syllabus. Now, this is not, it is not the syllabus only which is concerned over here. Okay, I'm concerned with the concept, that how this gravitation came into light, and how people understood it to a greater extent, to a better uh, understanding, so that the science could develop, and we are now today able to launch satellites into space. And because of our deeper understanding of the concept of gravitation, this has been possible. So for understanding gravitation in detail, we must know its historical perspective. So let's start with the time of Aristotle. So Aristotle was a Greek philosopher. Okay, so Greek philosopher Aristotle believed that an apple or any other object released from a height would fall down towards earth, because it was natural for any object to fall down towards earth. That was the belief. It is natural, like this kind of see, Aristotle was a very great philosopher, but this kind of you can say reasoning, it is very childish, that it is natural to for this to happen. And don't resort to these childish answers when some question like this is asked to you. And for upgrading our answer or to give answer with a scientific perspective, we must understand why any object falls down towards earth. Okay, it was thought that this fact needed no explanation because it was natural. Galileo in 16th century suggested that since earth is attracting object towards itself, therefore object fall down towards earth. So Galileo, for the first time, he suggested that Earth is attracting all the object towards itself. That's why everything falls down. Great minds not only think logically but have capacity to extend a simple idea to other related phenomena. Newton's greatness lies in his ability to see that the force responsible to attract apple to earth was the same force of attraction that operated between earth and moon, or between sun and planets. So he connected this simple idea of earth attracting object on its towards itself to, you can say, to the planets and to the heavenly bodies, that they also attract each other with equal and opposite force. Not only this, he expanded the idea further to include within its pure view of all material object. After analyzing Kepler's observation, Newton proposed the law of gravitation. So before Newton, the whole story started with Galileo. After Galileo came Tycho Brahe. Tycho Brahe, this guy, Tycho Brahe, in 16th century. See, Galileo was also from 16th century. Tycho Brahe was also from the same century. This guy, Tycho Brahe, he observed planetary motion for 20 years. He observed, see, this is some extra knowledge for you. Okay, so no need to remember all this, but just understand it in a manner that you know your basic understanding regarding gravitation is very very strong. Okay, so no need to remember all this, but just listen to it as a story and then relate with it when I give you the actual law of gravitation suggested by Newton. Okay, so Tycho Brahe, which was from the same century as of Galileo, he observed planetary motion for 20 years by simple instruments, as telescope was not invented at that time. Before the death of Tycho, he handed over the collected data to one of his students, Johannes Kepler. So Johannes Kepler was student of Tycho Brahe. Okay, so this Johannes Kepler, while analyzing the data, came to three important conclusions. He found some patterns, and the three important patterns which Johannes Kepler found were later known as Kepler's law of planetary motion. So before Newton could actually, put forward a universal law of gravitation, it was Johannes Kepler who, put forward Kepler's law of planetary motion. What is the first law of Kepler? Kepler's first law, that is law of orbit. It states that all planets revolve around the sun in elliptical orbits. Sun is at one of the foci of the ellipse. So as you see over here, this shape, this oval shape or oblong shape, this is known as an ellipse. In mathematics, this shape is known as ellipse. And every ellipse has two centers which are known as its focus or foci. Just a moment. Let me draw proper ellipse. This is like a disc. Okay, so this is an ellipse which I'm talking about. And every ellipse has got two centers, one over here approximately and one over here. These are the focuses of ellipse, and a focus or a center, it's is known as a foci in plural. So when there are two focus, it is known as foci. So how many focus does an ellipse have? Two. Okay, so sun is located at either this focus or at this focus. And what is this oblong or oval shape? This oblong or oval shape or elliptical shape or an ellipse. This ellipse is the imaginary path in which any planet revolve around the sun. So that is the first law of Kepler. What is the second law of Kepler? This is known as law of areas. Okay, so the line joining the planet and the sun sweeps equal areas in equal intervals of time. Okay, let's imagine that the planet is moving from P2 to P1. The planet is moving from P2 to P1. So let's join a line from P2 to the center, that is a focus, and P1 to the center. So what do you get? You get a triangle. Okay, so area of this triangle is equal to the area of triangle which is made by the moving planet, like just imagine the planet is moving when it is nearer to the sun at a faster rate. Okay, it always does that. So planet is moving from P4 to P3 in the same interval of time in which it moved from P2 to P1. In the same time interval it moved from P4 to P3. So here if you join P3 and P4 to the center, to the focus, then we'll get a triangle, or we get a you can say a sector of a circle. So area of this sector is equal to area of this sector. So this basically this area is equal to this area. So this is the Kepler's second law, that is law of area. So the planet and the sun, when are joined by a line, so this line you can say covers equal area and equal intervals of time. Okay. Third law of Kepler. See, you don't have to remember or go to the detail, or there are no formulae which will be, there are no numericals which will be asked on this part, but this is just for the historical perspective of gravitation, how it came about. Okay. And the third law is law of periods. It says that the cube of the mean distance of a planet from the sun is proportional to the square of its orbital time period, capital T. That means larger the radius, larger the distance of the planet from the sun, greater the time it will take to move around the sun. That means cube of the radius or cube of the mean distance of the planet from the sun is directly proportional to the square of the orbital time period. Larger the distance of a planet from the sun, greater the time it will take. But this is cube and this is square. Okay, so if the planet is far away from the sun, it will move, it will rotate, it will revolve slowly. But if the planet is nearer to the sun, it will revolve faster. Okay, so these were the three laws of Kepler, which basically started the whole journey of understanding towards understanding of gravitation. Okay, it was begun by Galileo in 16th century, also by Tycho Brahe, which passed it on to Johannes Kepler, who was the student of Tycho Brahe, and Johannes Kepler gave three laws: Kepler's first, second, and third law. Then came Newton in 17th century. So according to Newton's universal law of gravitation, this was very much refined. This was more refined because Kepler's laws were only restricted to our solar system, because Tycho Brahe studied the planets with his without any instruments. Okay, with simple methods he studied the instrument, and on the basis of that data, Johannes Kepler was able to make some important conclusions which were correct. But Newton, he connected these conclusions with a simple phenomena like apple falling from a tree with the heavenly bodies motion, or the behavior of heavenly bodies. Okay, that could be our solar system or any other solar system in the whole universe. That's why you can say Newton's view was much broader, much broader than Galileo or Tycho Brahe or Johannes Kepler. That's why Newton's law of gravitation is universal in nature, because it applies to every body in the universe. All the bodies around you, those are the, you can say, the bodies on the surface of the earth itself, all the bodies in the space, in the solar system, moon, earth, sun, all the planets, all the other solar system, Milky Way, galaxy, they all follow Newton's law of gravitation. And what is this law? So, many students, they asked me that we didn't understand the inverse square law. And here, that concept is also going to get clear. So, according to Newton's law of gravitation, every particle in the universe attract every other particle with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This law has to be memorized by you, but without understanding, if you memorize, you will forget very quickly. So let's try to understand each and every statement. So according to Newton's universal law of gravitation, every body in the universe attracts every other body. So let there be two bodies with masses m1 and m2, and the distance between these two bodies is r. So Newton's law of gravitation says that these two bodies will attract each other with a force F, that is known as force of gravitation, force of gravitational attraction. Okay, every body attract every other body with this force F. Now the two bodies in considerations are having mass m1 and m2, and the distance between them is r. So what Newton's universal law of gravitation states that uh, the force with which these bodies attract each other is directly proportional to the product of their masses. So force is directly proportional to m1 multiplied by m2. That means, what does this mean? That means that greater is the product of the masses of two bodies, greater will be the force with which they attract each other. Greater the force, greater will be the product of their masses, or greater the product of the masses, greater will be the force of attraction between the two bodies. And it states that it is inversely proportional to the square of the distance between them. So F is proportional to 1 upon r square, or inversely proportional to r square. That means if you double the distance between the two bodies, see what was r was the distance between two bodies, right, shown in figure 1. Where is the figure 1? Let's see. Yeah, so this is body 1 and this is body 2. Now what is the distance between them? R. Okay, so if r is doubled, if let's say r is made 2r. Okay, so if r is doubled, what will happen? The force is inversely proportional to the square of the distance between the two masses. That means if the distance is doubled, the force will decrease. If the distance is increased, the force will decrease, because this is inverse proportion. Inverse proportion means if one quantity increases, the other quantity decreases, right? If you must have studied direct and inverse variation in class 8th, right? So this is the same. If one quantity increases, the other decreases. This is inverse proportion. That means if the distance doubles, then the force becomes 1/4 F by 4. On the other hand, if the distance decreases, the force will increase. If the distance becomes half, then the force will become 4 times, and that is inverse square law. दिस इज नोन एज इनवर्स स्क्वायर लॉ. इसमें सिर्फ इतना ही याद रखना, अगर दो बॉडीज के बीच का डिस्टेंस डबल हो रहा है तो फोर्स 1/4 हो जाएगा, और अगर दोनों बॉडीज के बीच का डिस्टेंस हाफ हो रहा है तो फोर्स 4 टाइम इंक्रीज हो जाएगा. सो इफ डिस्टेंस इंक्रीजेस, force decreases. If distance decreases, then force increases. Acha, what if the distance becomes 3 times? If the distance becomes 3 times, then the force becomes 1/9. It will get divided by 9 of its original value. And if the distance becomes 1/3, then the force will become 9 times its original value. So what you do is, whatever multiple you multiply with your distance, you square that multiple, and then you reciprocal it, and then you multiply it with the force. So if I'm doubling the distance, that is, I'm multiplying 2 with the distance. So what is the square of 2? 4. So I divide the force by 4. If I multiply the distance by 3, let's say the distance becomes 3r. So what is the square of 3? 9. So I divide the force by 9. If I am multiplying the distance by 1 by 4, okay, so what is the square of 1 by 4? 1 by 16. So I multiply the force by 16, the reciprocal of 16. 16 times F. Okay, so that is inverse square law. So we know, and we now understand that if uh, uh, two bodies are kept in a space, the force between them, the gravitational force of attraction between them, will be directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay, now to let go of this gravitation of this proportionality sign and put equality sign in front, in the place of it, we need to introduce a gravitational constant. So we introduce a gravitational constant g. G is called universal gravitational constant because its value remains constant throughout the universe. Its value is the same anywhere you go inside, anywhere you go in the universe. Okay, so F, the final formula for the gravitational force of attraction between two bodies becomes F is equal to G m1 m2 product of the two masses upon r square, square of the distance between them, where G is universal gravitational constant. Now we have to find the value of G. Let's do that. See, gravitational force of attraction is because of the masses possessed by the bodies. So, what is the reason behind two bodies attracting each other? The reason is there. The reason is that because they possess masses. If they don't have masses, there is no gravitational force between them. Can you think of of an example where some quantity does not have any mass? Some quantity which does not have any mass. One example of a quantity which does not have any mass is light. Light does not have any mass. So is light attracted by any force of gravitation? No, light is never affected by the force of gravitation. Light travels in all the directions outward from, you can say, from a body which is emitting it. So if a body is emitting light, light will emit out of it and it will travel everywhere outwards in all the directions. So no force of gravitation will affect that light. Okay, so gravitational force is there because of the presence of mass. If there is no mass, there is no gravitational force. Okay, now let us find the value of G and the definition of G. What is G? Universal gravitational constant. Very important value. We had to introduce this universal gravitational constant because we converted this proportionality sign to equality sign. You remember in the previous topic, that is laws of motion, when we were studying about the formula for force, that is force is equal to force is directly proportional to mass and acceleration, right? So when we changed this proportionality sign into equality sign, what constant did we use? K multiplied by m into a, where the value of k for SI unit was taken as 1. So we came to a conclusion that force is equal to mass into acceleration. That should be the formula for force. Okay, but in this case the value of constant is not 1. Okay, so here G is universal gravitational constant whose value is not 1. So what is the value of G and how we can define G? Okay, see, this experiment was conducted by Newton with two gold balls. Okay, this experiment was conducted by Newton with two gold balls. Each of the ball was having a mass of 1 kg and the distance between them was kept as 1 meter. And if we put the value of masses and the distance as 1 in this formula, if mass becomes 1, each of the mass, and the distance between the two masses becomes 1, then F becomes equal to G. The force of gravitation becomes equal to the value of universal gravitational constant. And with the help of some complex calculations and experiments, the value of F, that is the force between the two gold balls, two 1 kg gold balls kept at a distance of 1 meter apart, was found out. And this value of F was the value of universal gravitational constant. So how can we define universal gravitational constant? The universal gravitational constant is the force of attraction between two point masses of 1 kilogram each kept at a distance of 1 meter. Okay, some important points which should be remembered regarding the gravitational force of attraction. The gravitational force of attraction does not change with the change in medium between the point masses. So if two point masses or any two bodies were kept on the surface of Earth or on the space, or in space, or on the surface of moon, or anywhere in the universe, the gravitational force of attraction between them does not change. Okay, if the medium is air, water, or vacuum, the force of attraction remains the same. Okay, refer to figure 2. Okay, so there is some one figure 2. Okay, this is the figure 2. You can see figure 2, mass m1 m2 is over here, f12 f21. Now can you tell me what is f12? What is f12? F12 is force exerted by, sorry, force exerted on body 1 by body 2. On body 1 by body 2. So can you now similarly tell me what is F21? F21 is force exerted on body 2 by body 1. So this force is exerted by this body. So this force is, pulling this body M1 towards M2. And this force is exerted by body M1. It is pulling body M2 towards M1. Okay. So the second point which you must remember is F12 is the force on mass M1 due to M2. F21 is the force on mass M2 due to M1. It has been found that this force is equal and opposite. So these two forces form action-reaction pair. Now you already have studied Newton's third law of motion and you know what is an action-reaction pair. Action and reaction pair are pair of forces which are equal and opposite, and they act on different bodies. And here we have two different bodies, M1 and M2. On body M1, the force acting is F12, and on body M2 the force acting is F21. Okay, so these forces are equal and opposite, so F12 is negative of F21. This means that Newton's law of gravitation obeys Newton's third law. Third point to be remembered about gravitational force of attraction: it is the weakest force in nature. It is the weakest force in nature, and it is always attractive. It is always attractive. Okay, it is the weakest force in nature and it is always attractive. It obeys inverse square law, that is, force is inversely proportional to the square of the distance between two bodies. If the distance between two bodies doubled, the force will become 1/4, and if the distance between two bodies is halved, then the force will become 4 times. Okay, it obeys inverse square law. Gravitational force is a central force. This means that this force acts along the line joining the centers of the particle. Okay, so I want you to take notes of whatever important things I'm speaking over here and which is written on your screen. I want you to pause the video in between and take notes, and on the basis of these notes you are going to form the answers. Okay, so it is very important that you keep on taking note while I'm teaching. Don't just listen. If you have not taken any notes yet, just go back to the beginning of the video, listen to every important thing which I have just mentioned, and take notes. Okay, no need to take notes on that historical perspective. If you want, you can take, but no compulsion regarding that. You need to start taking notes from Newton's law of gravitation, Newton's universal law of gravitation. Okay, the seventh point to be remembered is gravitational force is a long range force. It is also applicable between the galaxies. Okay, now note one small thing. D, that is distance between the two bodies, is replaced by capital R in case one body is Earth and the other body is on the surface of Earth. Similarly, small d is replaced by small r if one body is a satellite orbiting in a radius of small r and the other body is the Earth or Sun. The formula becomes F is equal to g m1 m2 upon r square, or F is equal to g m1 m2 upon small r square, where r is, what is r? Radius of Earth. And what is this is capital R, and what is small r? Small r is radius of orbit in which the satellite is revolving. Okay, so this is basically the meaning of the formula. Okay, we have not yet still talked about the value of g. Let's find out the value of g. The value of g comes later. Okay, effects of gravitational force. You see the tides in the ocean. Why do oceans have tides? These tides are the result of gravitational force between the water in ocean and the moon. You must know that by now, because moon has different positions. It is also continuously revolving in a orbit around earth, so it has different position with respect to different positions. It has different position with respect to different locations on earth. So wherever the moon is near, there is a high tide, and wherever the moon is far away, there is a low tide. So since earth is revolving on its own axis and moon is doing revolutions around earth, what happens is the moon comes to the same location again and again, you can say twice a day. So twice a day there is high tide, and twice a day there is low tide. Okay, so because of the attraction of moon, because of gravitational force between water in earth, water in the oceans of earth and moon, there is this high tide and low tide. Of course, the gravitational pull of earth keeps a satellite orbiting around the earth. There are so many satellites which are orbiting around the earth, which are basically communication satellites, or they are weather satellites. Some are geostationary satellites, some are yeah, I think orbital satellites, and there are different kinds of satellites. They all keeps on orbiting the earth because of the gravitational pull of earth. Rainfall and snowfall is also possible because gravitational pull of earth. Otherwise there would not have been any rainfall or snowfall. Okay, so these are some effects of gravitational force. Now let's talk about value of g. See, first I will start with the learning plus part. The value of g, universal gravitational constant, could not be found when Newton gave the law of gravitation. It was only 100 years later. Yes, so this is important. I by mistakenly told that Newton did this experiment of gold balls, but 100 years later, the truth is 100 years later, Henry Cavendish was able to measure the value of g using that gold balls experiment. That is the story behind it. I want all of you to research that how this value was measured, how the value of g was measured. Okay, we are coming to the value, and I'll also show you the formula with which the value was found. But uh, yeah, we have already discussed that formula, but I want you to get the story behind the measurement, or you can say the discovery of that actual value of g. Okay, Henry Cavendish was able to measure the actual value of g. Tides formed in sea is due to the gravitational force of attraction of moon and sun on seawater. We already know that. Okay, so the value of g was initially determined by Henry Cavendish in 1798 by using an instrument called torsion balance. Wow, the description of torsion balance is beyond the scope of this book. Okay, so don't expect that you will understand what torsion balance is now, but yeah, you can definitely see some videos on that and read some articles on that. It's good for your extra knowledge. The presently accepted value of g is 6.67 into 10 raised to minus 11 Newton meter square per kg square. Mathematically, we can say that because of small value of g, gravitational force are the weakest force in nature. Now let me let me at least give you the idea about how this value of g comes to existence. So we know that the force due to gravity, or gravitational force between two bodies of mass m1 and m2, is g m1 m2 upon r square. Now what did we take? We took m1 and m2 as 1 kg, and we took r as 1 meter. Okay, m1 m2 is 1 kg and r is 1 meter. So uh, it is found that f becomes equal to g in this case, right? Because this m1 m2 are all become unity. Okay, but their units do not just disappear. that their units do not just disappear. So what we find here is the unit of mass is kilogram. So we have kg square upon the distance, that is the distance between two bodies in is in meter square, so per meter square. Okay, and here we have, in place of force, we have 1 Newton. Okay, this is 1 Newton. So G multiplied by 1 kg square multiplied by 1 per 1 meter square. Okay, now can we find the uh, okay. I'm sorry. This was not 1 Newton. This was measured with the help of the torsion balance thing as 6.67 into 10 raised to minus 11. So the force of the gravitational force of attraction between two bodies of masses 1 kg placed at a distance of 1 meter apart was found with the help of that experiment by Henry Cavendish to be approximately equal to 6.67 into 10 raised to minus 11 Newton. Now we put the values of the force, of the masses, of the distance between them, everything, and now we find the value of G. So what does G become equal to? Now this kg square will go to that side, so it will become 6.67 into 10 raised to minus 11 Newton. Okay, this meter square, per meter square goes to that side, becomes meter square, and this kg square goes to that side and becomes per kg square. So G's value is 6.67 into 10 raised to minus 11 Newton meter square per kg square. Whatever happens, don't forget this value. Okay, don't forget this value. Now you know what happens is many students, they come for admission with me, and they have this interview with me, and in every interview I have asked the value of G, that is universal gravitational constant, and only a few students they were able to answer that what is actually the value of G, that is the value of universal gravitational constant. Okay, so please remember this value, and please also remember the method with which I found this value. Okay, let's go ahead. So the next thing which I wanted to tell you was the small value of G. Now do you see how small is this force? This force between two bodies of mass 1 kg kept at a distance of 1 meter from each other is so small that if I write it in decimals, it will look like this. Uh, yeah, this much Newton of force is gravitational attraction force is there between the bodies of two masses. It is not even appreciable, it is negligible force. This force is negligible, and because the force between two bodies of mass 1 kg kept at a distance of 1 meter apart is so negligible, we can say the value of G is very small. And since the value of G is very small, we can say that gravitational forces are weakest forces in nature. And further, they have written that it is because of the small value of G that the force of gravitation between small masses is negligibly small. Two objects kept on a table do not move towards each other because the gravitational force is unable to overcome the frictional force. तुम्हारे टेबल पे अभी दो चीजें रखी है, सपोज दोनों का मास 1 kg है, एंड कीप देम नियर ईच अदर, विल दे मूव टुवर्ड्स ईच अदर? Will they attract each other? They should not be magnets, okay? They should be normal objects. Will they attract each other? No, because the force between them is very, very small. It's so small that the frictional force which they are, facing right now, it is greater than the gravitational force between them. That's why they do not attract each other. Okay, so it becomes appreciable only when at least one body is huge like the earth. So gravitational force between earth and any body is so huge that if you drop anything, just hold an object in your hand and drop it to the ground and just see how it falls down. It is not falling down, it is actually getting attracted by the earth towards the earth. the earth is attracting that body towards itself. And how fast is it falling? It's falling so fast because earth is a huge object and the other object which is in your hand is a very small object. That's why the gravitational force becomes appreciable. Okay, otherwise the gravitational force between two small bodies is always very very weak, and gravitational forces overall are very very weak forces in nature. They are the weakest force in nature. Okay, let's start with some numericals. Okay, the first numerical is, what is the force of gravitation between two point masses of mass 1 kg and 2 kg kept 1 meter apart? Okay, so m1 is equal to 1 kg, m2 is equal to 2 kg, and the distance between them r is 1 meter. Okay, so we can say that the force between them is equal to g multiplied by m1 m2 upon r square, which is 6.67 into 10 raised to minus 11, which is the value of g, multiplied by 1 into 2, both are in kg, both are in SI units, upon 1, that is 1 square, I'm sorry, that is the square of the distance between them. Okay, now what? Now it comes to, simply comes to 6.67 into 10 raised to minus 11 multiplied by 2. Now if some students are afraid looking at these figures, this is known as scientific form of a number, 6.67 into 10 raised to minus 11. You should not be afraid, because you should be afraid when a number is written like this. You should be thankful that the number is not given in this form, otherwise the calculation would become very very complicated. So you should be thankful that we are using scientific form in physics, so that the calculation will become, as you see now, it will become very easy. So now what you will do is, you keep this power of 10 separate, and you multiply the two numbers which are there with you, that is 6.67 multiplied by 2 multiplied by 10 raised to minus 11, and this is in Newton. Okay, now you just do the calculation of 6.67 multiplied by 2 and get the answer, and I will confirm your answer. Okay, so pause the video and do the calculation if required. Okay, I hope you have done the calculation. The final answer comes to be 13.34 into 10 raised to minus 11 Newton. That is the force of gravitation between the two point masses, which is very very small. Okay. Now do you know that this number which you have, it is the correct answer, but still it could have been expressed in a further in a proper scientific form. See, to express it in scientific form, what we'll do is we'll move this decimal point from here to here. So always we make sure that we move the decimal point to the right of the first non-zero digit, to the right of the first non-zero digit, and first non-zero digit is 1. So the number becomes 1.334 multiplied by, now since you are moving the decimal point to the left side, now what you will do here, you will add 1 to this power. So minus 11 plus 1 will become minus 10. So 10 raised to minus 10 Newton. So this is also the correct answer, and this is also the correct answer. But the last answer which I have written, this number is in its proper scientific form. Okay. So 1.334 into 10 raised to minus 10, or 13.34 into 10 raised to minus 11, and which is an extremely small force between these two bodies, and that's why they don't seem to attract each other when they are kept on a surface. Next question. What is the force of gravity acting on a point mass 1 kilogram released from a height of 1 meter from the surface of Earth? Okay, so here one body which has the mass of 1 kilogram. The other body is the Earth itself. So mass of Earth is given in the question. See, they are giving you this information. 6 into 10 raised to 24 kg. This is approximate mass of Earth. Okay, and the distance between Earth. So here comes the main point of learning. Okay, now understand this. If you are considering Earth and an object which is okay, if you are considering Earth and any object which is at the surface of the Earth or near the surface of the Earth, the distance between Earth and that surface has to be taken from the center of Earth. Okay, so in this case, the distance between surface and center is the radius of Earth. So, what is the radius of Earth? The radius is 6.4 into 10 raised to 6 meter. Okay, 6.4 into 10 raised to 6 meter. Now, will it be okay to add 1 meter? Will it be okay to add 1 meter? Will it make any difference if you add 1 meter or not? It will not make any difference because 1 meter and 6.4 into 10 raised to 6 meter, they have no comparison. 6.4 into 10 raised to 4, that is the radius of Earth. It's a huge distance. Just imagine the size of Earth. And 1 meter is somewhere over here, not over here. I'm maybe 100 kilometer above the surface of Earth by now. So this point which you see, blue point, is very far away if you consider Earth to be a very small sphere. So 1 meter is very, very near to the surface of Earth. So we don't consider that distance. Okay, we consider the radius to be the distance between the Earth and the object at the or near the surface of the Earth. So the what is the force of attraction between this object and the Earth? Force of gravity. Okay, that is force of attraction exerted by Earth is known as force of gravity. So gravity is a special phenomena which is only due to Earth's force of attraction, Earth's gravitational force of attraction. So force of gravity is equal to G m1 m2 upon r square. Let's put the values. 6.67 into 10 raised to minus 11 multiplied by m1, which is 1, multiplied by m2, which is 6 into 10 raised to 24, upon r square. What is r square? 6.4 into 10 raised to 6, the whole square. So what we will do now? Now we will simplify this, and here you have to learn a lot of things regarding calculations. Many students are going to find issues with the numericals of gravitation, but if you see this working, which I'm just going to show and discuss with you, you will, I promise that you won't have any issue. Okay, so just focus on this. So F is equal to G, which is 6.67 into, okay, I'll write the number next to it, which is 6 multiplied by 10 raised to minus 11 multiplied by 10 raised to 24, the whole upon 6.4 square, that is 6.4 multiplied by 6.4 uh, multiplied by 10 raised to 6, the whole square, that is 10 raised to uh, 10 raised to 12, correct? Because 10 raised to 6, the whole raised to 2 is 10 raised to 6 into 2, that is 10 raised to 12. 6.4 square is 6.2 written 2 times. Okay, so we have F is equal to, now I'll write the numbers all together. 6.67 into 6 upon 6.4 multiplied by 6.4 multiplied by 10 raised to minus 11 into 10 raised to 24 is nothing but 10 raised to 13, the whole upon 10 raised to 13, the whole upon 10 raised to 12. Do you see that? Do you see that? Okay, so now what? Now we are going to simplify the whole thing. So what we have to do is we have to cut these things as far as possible. So 2 3s are 2, 3.2s are, correct? Can anything be cut now? Nothing can be cut. Can this be simplified? Yes, it can be. So F is equal to 6.67 multiplied by 3, the whole upon 3.2 into 6.4, which is, I almost forgot. Okay, so multiplied by 10 raised to 13 upon 10 raised to 12. Remember exponents and powers. So this will become 10 raised to 13 minus 12. That is 10 raised to 1, which is nothing but 10. Okay, so this will become, see, now what I'm going to do is I'm going to remove decimal places. So in the numerator, if I remove two decimal places, in the denominator I can also remove two decimal places. By what? By multiplying 100 in the numerator and denominator. So if you multiply 100 in the numerator and denominator, you are not changing the value, but what you are getting is this: 667 multiplied by 3 multiplied by 10, 10 remains as it is, the whole upon 32 multiplied by 64. Now I will not help, because the steps in which I have helped is from this step, and I brought it and I made it simplified up to this step. Now multiplications and division should be easier for you. So please find the final answer. Please find the final answer, and we will verify after a while. Okay, so pause the video, write this much, and find the final answer. Okay, so I think you have got the correct answer. The answer which I am getting is 9.77, 9.77 Newton. So you can say that a body of mass 1 kilogram will be attracted by Earth with a force of 9.77 Newton. Let's check the answer. 9.7 Newton. That's what they are getting. So this, what they are saying is this is an appreciable force. We neglected the height 1 meter because it is very small as compared to the radius of Earth. So if out of two masses, one is Earth, the force of gravitation is called force of gravity. Right? These all things we have discussed at the beginning of solving this example. Correct? Third example. Okay, let's go to the third one. See, your concept will become absolutely clear regarding the formula of gravitation. That is the first thing you should understand, and then there are other things which are important, which we will discuss later. But the first thing is understanding the formula of force due to gravitation, and then applying it in the numericals. That's what we are doing. Okay, calculate the force of gravitation between Earth and the Sun. Simple. One body is Earth, other body is Sun. Both masses are given, Earth and Sun masses, and the average distance between the two is also given. Why average distance? Because we just saw Kepler Kepler's study showed us that the path in which any object, any planet moves around Sun is elliptical. So the distance between Earth and Sun is sometimes very less and sometimes very large, right? So the average distance between the two is 1.5 into 10 raised to 11 meter. So what is the force between them? So the force between them, sorry, the force between them is G multiplied by m1 m2 upon r square, which is 6.67 into 10 raised to minus 11 multiplied by 6 into 10 raised to 24 multiplied by 2 into 10 raised to 30 upon the whole upon r square, that is 1.5 into 10 raised to 11 the whole square. Okay, now we need to simplify this. Again, I'm going to help you. Okay, so first we'll write 6.67, then which is the next number, not the power of 10, the number. The number is 6 and then the number is 2. So you write 6 and then you write 2. Then you list all the powers of 10. 10 raised to minus 11, then 10 raised to 24, then 10 raised to 30, and in the denominator you write 1.5 multiplied by 1.5 multiplied by 10 to the power 11 the whole square, that is 10 to the power 22. Correct? Okay, now what? Now you need to cut. So basically this uh, 6 gets cut with 1.5, by the table of 3. So 3 2s are 6 and 3 0.5s are 1.5. Can we cut 1.5? See, it will become 0.75, so don't cut if you don't want. It's okay. All right. So we get 6.67 multiplied by 4, 2 2s are 4, upon 0.5 multiplied by 1.5, which is 0.75. Okay, multiplied by, okay, here you will get 10 raised to minus 11 multiplied by 10 raised to 24 multiplied by 10 raised to 30 multiplied by 10 raised to minus 22. This 10 raised to 22 comes up, becomes 10 raised to minus 22. Okay, here if you multiply 100 in the numerator and denominator, this will become 667 multiplied by 4. I just removed the decimal places, and in the denominator also I multiplied by 100, so it will become 75 multiplied by, here add all the powers. So 24 plus 30 is 54. 54 minus 33. Okay, 54 minus 33 is 21. Yes, 21. Okay, so this will become 10 raised to 21. Okay, now use your calculation skills, not the calculator. Use your calculation skills and find the answer to this. Pause the video and find the answer. Okay, so the answer should be 35.57 into 10 raised to 21 Newton, which is a huge force. Why this force is so large? 10 raised to 21 means what? 3557 and in front of it 19 zeros. That means it's a huge force between Earth and Sun because these bodies have huge masses. Let's check the answer. 35.57 into 10 raised to 21 Newton. This force on Earth, which is responsible in keeping the Earth in its orbit around Sun, and this force works even when the masses are at a distance of the order 10 raised to 11 meter, which is a huge distance between Earth and Sun. Even light takes around 8 minutes to reach from Sun to Earth. Therefore, gravitational force is termed as a long range force. This is the proof of it. At a long range also it is so strong. But still it is the weakest force in nucleus, in the universe, because the value of G is very small. It is not even appreciable for normal sized bodies. It is only appreciable for heavenly sized bodies. Okay, just a little bit of trivia for you. We do not observe small objects moving towards each other because of gravitational pull. This is because frictional force balances the gravitational pull. It does not allow the objects to gravitate towards each other. Had the value of G been 100 times its value, its original value, then you would have been crushed due to the force of gravity. Simply the force of gravity would crush you at the moment, so you would not be able to exist on this planet. Okay, but the value of G, uh, remember that if the value of G becomes 100 times its present value, the force also becomes 100 times. So your own weight becomes 100 times of itself. If your weight right now is, let's say, 50 kg, it will become 100 times of 50 kg. That is 5000 kg, and you would be crushed with your own weight. Had the value of G been 1 by 100 times its value, then you could easily jump from a multi-storied buildings because your velocity would have been very small while reaching the ground. The velocity with which your body reaches the ground will be very small if the value of G had been 100th time its value presently. So this is just trivia for you to imagine that how value of G is responsible for the force due to gravity. Okay, so that was the first part. I'm not giving you this exercise. This exercise is meant for some other students, and that is CBSE students. For ICSE students, already they have exercise in their textbook. The next topic is acceleration due to gravity, but I don't want to go to this topic immediately because I want students to first understand the first part properly, and then we can go to this acceleration due to gravity part in the next video. Till then, just go through the topic which I have discussed till now, and uh, there is no homework, but take notes. Definitely take notes. Okay, I'll see you in the next video. Bye bye.